In this video I will go through ISP task 3 on the Astrophysics ISP for unit 5 of Edexcel Physics, which is the last unit of the A2 year. So you can see that for task 3 it is just reading through the equations list of unit 1, 2, 4 and 5, listing all the variables, and next to each variable writing a symbol of the unit. So you can do that in your own time. Remember to use the equation list in here to help you out, and also complete the task 4 questions. Let's go straight to task 4 questions and see what they're all about. So task 4 questions, here we go. So it's just because on my old ISP it was linked to a different task, so this time's task 4, you'd assume it would be task 3, but it's task 4, never mind. Anyway, so the first question is asking about satellite, okay, and they're saying the satellite's in a geostationary orbit around the Earth. So remember, if an orbit is geostationary, what that is telling us is wherever you look in the sky, the satellite will always be in the same spot, so it's always in the same point above the Earth's surface, no matter what. So I'm just bringing up my notes on this. Okay. So write down an expression for the gravitational force of the satellite with the mass m in an orbit radius r around the Earth with a mass capital M. Okay. So essentially, the equation we're after is F is equal to G n little m over r squared. Okay, it's an inverse square law. The force is an inverse square law. Hence, derive an expression for the gravitational field strength at a distance r from the centre of the Earth. Okay. So we're looking at a specific distance from the centre of the Earth, and we're trying to figure out small g from this. So we're going to need to use a different expression. So the expression we're going to use is weight is equal to mass times by gravity. Weight is the force in the situation. Okay, so what we can do is rearrange that now for g if we wanted to, and then sub in our f afterwards. So g is going to be equal to f over m. Okay, so that's going to be g big M little m over r squared over r over m, sorry. Well, that m and that m cancel out, so g is equal to gm over r squared. Okay. There's only one mark attached to that question. Use this together with an expression for centripetal acceleration to show the radius of a geostationary orbit is given by r cubed g m t squared divided by 4 pi r squared. So I've done this derivation or a derivation similar to this in a different video. So let's go through this one step by step. So a is equal to v squared over r. Okay, that's one of the expressions that we're given. Sorry, let's bring this back to shop. A is equal to v squared over r. So that's one of the expressions that's given in our pack in the equation list. Well, a in this situation is g. The acceleration is caused by gravity. So a is equal to, so g, sorry, is equal to v squared over r. Well, let's sub that in straight away. So we end up with v squared over r is equal to g m over r squared. Well, we don't want v, because I haven't got a v in that one, but we want to get t in there somehow. So you know that v is equal to 2 pi r, distance, i.e. circumference, over time, with time period. So a complete circle divided by the time to go around the complete circle, the time period. So v squared is going to be equal to 4 pi squared r squared over t squared. So let's put that in. So you end up with 4 pi squared r squared over t squared divided by r is equal to GM over R squared. Well, we want to get rid of this R over here, of course. That's going to cancel one of those R's from there. So this disappears, and you end up with that. Then it's just rearranging. So if you were to rearrange this, you end up with 4 pi squared R times by R squared, so that ends up being R cubed. Okay, put that on top, is equal to T squared GM. So we've got everything on one line there, which makes it nice and easy to rearrange from. We want R cubed, so let's bring this bit underneath here. So this bit disappears, and it ends up down here instead. That's exactly what they want. Okay, so we've just got the GMT, they've written it that way around, we've just got TGM that way around instead. So it's a nice question to get, common derivation, make sure you can do it. So it's 3 marks. Play that part of the video back through if you need to get your head around that derivation. Calculate this radius. Okay, so we've got the mass of the Earth. Okay, so you're going to want R, so literally just plugging the numbers in. You know G, it's a constant, M has been given to you, T is the time for the orbit. Okay, so if it's geostationary, that's going to be 24 hours. You need to get that T into seconds. Okay, and 4 is a constant, as is pi. So it's a pretty straightforward calculation to do there. So you should end up with something along the lines of 4.2 times 10 to the 7. Okay, so remember that's a constant, G is a constant, M is a constant, they give it to you here. T is 24 hours in seconds, so that's 24 times 60 times 60. Okay, and this is constant underneath. Nice question to get, very simple question to get, but most people will be able to answer that question correctly. Remember, you're doing a cube root though, that's where people are going to mess up in that. The mass and speed of the satellite do not appear in the above equation. Explain whether a satellite could remain in a geostationary orbit with a greater mass. Well, yes, because in a geostationary orbit, the R is constant, so the acceleration will remain the same regardless of the mass. The mass is not affecting the acceleration. With a greater speed, okay, no, it wouldn't, because for a geostationary orbit, T and R are fixed, so you can't increase V. Okay, so in a geostationary orbit, these two values here are fixed. T and R are fixed. So if you changed V, you're technically changing T and R, because the other things in that equation are constant. So V cannot change. Okay, in this situation, T and R are fixed values for geostationary orbits. So V cannot change because the only things that V depend upon are T and R. Therefore, greater speed is not a possibility. Explain why a satellite has to be over the equator to remain in a geostationary orbit. You can use a diagram to help your explanation. So what you've got to remember is that the center of the satellite's orbit must be the center of the Earth. Okay, that's the idea of a geostationary orbit. So the center of this orbit must be at the center of the Earth. Okay, there must be a common axis of rotation for the satellite and the Earth. Okay, so they must rotate around a similar axis. So the Earth is going to rotate around its axis here, and as is the satellite. And therefore the satellite's orbit must be at right angles to the spin of the axis. Okay, so that's why it's always over the equator. So the first thing is that it must always be over the center of the Earth, and they both have a common axis. That's the reason why it's a geostationary orbit. The geostationary orbit, is directly above the equator. Right, communication satellites often place geostationary orbit. Another question about geostationary orbit. The speed is given by the expression V is equal to omega r. So that's another way of writing V is equal to 2 pi r over t, where r is the radius of orbit. A student calculates that omega has a numerical value there. Show how he arrives with this figure. Well, we've got V and R in that situation. However, we haven't got a way of figuring out V yet, or so we think. Now, if you look back at our previous question, we've got this expression for V that's given to us. So that will allow us to figure out our V. Okay, R is the radius of the orbit, but once we sub it into here, it will actually disappear. So V to T technically ends up just being 2 pi over T. And T for geostationary orbit is 24 times 60 times 60. So let's make that really clear. We want omega, So omega is going to be equal to V over R. That is equal to 2 pi R over T, all of that divided by R. The R's cancel, so omega is equal to 2 pi over T. Okay, and that's how we can figure out the value of omega. State the unit of omega. Okay, so it's per second or rads per second. Either of those will get you that final mark. Hence, otherwise, calculate the height of such satellites above the Earth's surface, given that the Earth has a mass of 5.98 times 10 to the 24 and a radius of 6.38 times 10 to the 6. So, big question. Okay, so we've got a few expressions to use for this, so I'll guide you through it on the mark scheme. Just gone past, I think. Yep, that's just the one that we did previously. So there we go. So we've got to use the idea of F is equal to G M over R squared is equal to mv squared over R. So that's essentially saying something that was mentioned in an earlier video. So it's essentially equating the centripetal force to the gravitational force over R squared is equal to mv squared over R. Okay, and that's the easiest way to approach this. So we know G, okay, we know the mass of the Earth, the mass of the satellite disappears, we will know the height above the Earth's surface, so we will know the radius. Once you've calculated the radius, you need to take that away from the radius of the Earth. Okay, so velocity we know, okay, so it's straightforward, so we know that one, so therefore we'll calculate R. So the idea, what you actually end up with, is that R, I think we've even got it on the last slide from one equation that we figured out before. Yeah, R cubed. We could actually go with that equation actually, it's probably slightly easier. If we went straight with this equation over here, that we figured out, let me move it across slightly. Where is it, where is it? Yep, this one here. Again, still out of shot, there we go. So we can figure out R from this. We know what the time period is, we know what G is, we know what M is, we know what 4 pi squared is. Okay, so if we want this expression that we use in a similar question that we derived from a similar situation, okay, we can figure out our R. As soon as we've got our R, we take that away from the radius of the Earth to figure out the height. That's pretty straightforward. Okay, so you could do it the way that we were just about to do it, where you do that, so those equal to each other, cancel out your M's, okay, and therefore figure out the expression that they have here, and then just put your value straight in. But that's exactly what they've just done here anyway, which is what we've figured out. Pretty straightforward. Sorry, not pretty straightforward, but if you get it, you can get it done quite quickly. That's a question that other people won't be able to do, that you will be able to do. Okay, next. Wien's law calculation. Nice and easy. State what is meant by each symbol and weight in Wien's law. Okay, so remember in Wien's law, we're assuming objects are black bodies whenever we use it. So T is the temperature and lambda max is the maximum wavelength. Okay, so remember in this situation we've got to assume, so it's the maximum wavelength of a peak intensity. Okay, so that's the wavelength of peak intensity, and that is temperature. And remember that temperature is measured in Kelvin. Okay, so it's the temperature at the surface. So not anywhere in the star, but mainly at the surface. So it's temperature in Kelvin at the surface, and that is the wavelength of peak intensity. Okay, or we could say peak brightness, but don't say peak power. Peak power would be incorrect. Peak brightness would be okay, but peak intensity would be better. Right, so we've got a graph of a COBE satellite. Okay, you've got wavelengths here in millimeters. Okay, so you've got the COBE satellite, and you should know a bit about the COBE satellite. You know that the COBE satellite was mainly looking at CMBR and those sort of ideas. But you can see there's a wavelength in millimeters, and wavelengths in millimeters normally belongs to the microwave part of the spectrum. Use a graph to determine the temperature of the transmission source. So again, we're using Wien's law. It's about 1 or 1.05 millimeters for that peak emission. And when you put that through, you end up with about 2.76. Now, you possibly should know that background radiation, which is microwave, cosmic microwave background radiation, has a temperature of about 3 degrees Kelvin. Or sorry, I shouldn't say degrees Kelvin, 3 Kelvin. So getting 2.76 Kelvin is a very good answer to this question. A star is considerably more massive than the Sun. ends in a supernova. During a supernova explosion, 1 times 10 to 46 joules of energy can be released. Huge amount. State the minimum mass of a star that can be a supernova. So we generally say 8 times more massive than the sun. Okay, so the way you'd write that nice and quickly is 8, and that's mass of the sun. So 8 times more massive than the sun. So the circle with a dot in it is a shorthand for the sun. Right, so we've got the luminosity of the sun, and we've got the approximate lifetime of the sun, and they want us to figure out the energy. So that's power and that's time. So energy is equal to power times by time. But remember, you've got to turn the time into seconds. That's the only thing you've got to be aware of here. When you do the years part of this, a year is 365 and a quarter days. Okay, so you multiply 365 by and a quarter by 24 by 60 by 60 time, and that is 3.9 times 10 to the 26. And you should end up with about 1.2 times 10 to the 44. Estimate the ratio of energy that is released when a supernova explodes to the total energy given off by the sun during its lifetime. Okay, so that's just one of those numbers over the other one of those numbers. Okay, so you end up with a ratio of about 83 to 1. Okay, if you were to do that. Check which way around I want the ratio, supernova to sun. So sun will be the smaller of those two values. Sun will be the 1 and 83 will be in front of it. When a supernova explodes, the mass of its core remnant determines its future. State the 2 possible outcomes, and each depends on the mass of its remnant. Okay, so remember we've got a neutron star or a black hole. Okay, so a neutron star. Neutron stars are formed, okay, if it's generally greater than 1.4 times the mass, and a black hole is if it's 2.5. If it's greater than 2.5 times the mass. Right, next one. There are 2 facts that you need to know. Right, so neutron star density is what they're after in this next question. Okay, they're after the density of this neutron star. So they've given you some information here about the mass of the Earth and what it would be like if it was a neutron star. Okay, so if the Earth had the same density as a neutron star, it would be approximately 150 in meters in radius. Show that the average density of such an object would be about 4 times 10 to the 17. Okay, so what we're talking about here is neutron star density, essentially. So remember, density is equal to mass per unit volume. So that's going to be the mass that we've already got, and the volume is going to be 4 over 3 pi r cubed, and that's the cube that we've already got. That's pretty straightforward. So just plug your numbers into that. Should end up with about 4.2 times 10 to the 17. Explain how neutrons in a neutron star were formed, both during and after the main sequence. Okay, so in main sequence, remember you have the fusion reaction that takes place, and that fusion that takes place in the main sequence turns protons into neutrons, and the process involved in that is beta plus decay. It's not beta minus, but beta plus instead. So remember you have the ideas of a proton plus an electron essentially ends up with a neutron afterwards. So gravitational collapse or implosion is the idea that generates these conditions that cause this to happen. Right. Use the data below to calculate the intensity of the sun as measured from Mars from the Earth. Okay. So that is just the equation of I is equal to L 4 pi over d squared. So remember that's sometimes R, that's sometimes F. Okay, and it is just subbing in the values that we actually have. for the different planets. And what you should end up with is, so I'm just trying to find where I've written these down, 597 and 1380. Yeah, 597 and 1380. So Mars is 597. So I haven't written down which one's which planet, but obviously Mars will be the one that's less intense. 597 is Mars, and 1380 is the Earth. Okay, so it is just subbing it into this equation here. Nothing more than that. Okay, hence show that the brightness of the Sun as seen from Mars is approximately 40% of its brightness from Earth. So that's just dividing one by the other in terms of like an efficiency calculation, and that's pretty straightforward. Okay, next. So we've got the Sun, we've got the Earth going around it, not drawn to scale. I'm saying the line between the Sun and the Earth is at a point P where the gravitational field strength of the Sun is equal and opposite to that of the Earth. Point P is at a distance r from the centre of the Sun and a distance r from the centre of the Earth. So it's much further away from the Sun than it is from the Earth, although it's not to scale. The mass of the Sun is ms, the mass of the Earth is me. Excuse me. The gravitational constant is g. Using the symbols, right? The gravitational expression of gravitational field strength. That's pretty straightforward. Gravitational field strength of the Sun at point P. Okay, so gravitational field strength G is going to be Gm s over r, big R squared, of the Earth, G m e over little r squared. Okay? They're not after the force, they're after gravitational field strength. The mass of the Sun is 2 times 10 to the 30. The mass of the Earth is 6 times 10 to the 24. Show that the ratio of r to r is about 600 to 1. Okay, so the idea is you need to equate these two, because we know that these two are equal in size. That's what they told us. Sorry, let's get this clear. These two are equal in size, which is what they told us. So we know that g ms over r squared is equal to g me over little r squared. Well, they want the ratio of r to r. So we want to get r over r. We want to get big R over little r. Okay? So when you bring that on top and bring that underneath, the g's cancel because they're both constants. So essentially, ms over me is equal to r2 squared over r squared. If I square root both of those, if I square root this side, the r's disappear, so we have to the square root of this bit over there. Okay, and then we'd go from there. Okay, and that gives us the correct answer. Hence, find the value of r given that the distance from the centre of the Earth to the centre of the Sun is about 1.5 times 10 to the 8. Okay, so you're going to do 1.5 times 10 to the 8 times by 1.5 times 10 to the 8 divided by this idea of 601. That will tell you what 1 is equal to, and then you multiply that through to get your answer for what the r is, because you can figure out that 1 is 600 times bigger than the other. So if you've got 1 on one side and 600 on the other, so if you know what the whole distance is, you can figure out what each one is individually. You should end up with about 2.5. Okay, so 1.5 times 1.5 times 10 to the 8, which is the value they've given us there, divided by 601, and then multiplied through. Straightforward as that. So last question, talking about SOHO. A satellite that monitors the Sun is positioned at a point on a line between the Earth and the Sun. The gravitational forces acting on it keep it in the same relative position orbiting the Sun at the same rate as the Earth. On the diagram opposite, mark a point L as a possible position for SOHO. With reference to circular motion of SOHO, explain how you decided on the position of L. You are not expected to perform any calculations. So L, if we look back over here, is going to be somewhere around P. Okay, well, somewhere to the left of P. Okay, it's going to be on this side of P, and this is due to the fact that the force due to the Sun must be greater than the force due to the Earth, otherwise it will just stay there. Okay, so if it's on this side, the force due to the Sun is greater. If it's on this side, the force due to the Earth is going to be greater. So it's going to be on this side because the centripetal acceleration must be towards the Sun. Okay, centripetal force must act towards the Sun, so it rotates this way around. You can see my mouse going around the Sun. If it's rotating this way around, okay, it's going to be closer to the right hand side of P because the centripetal force must be acting towards the Sun. Well, they want it rotating this way, as described in the question. Centripetal force must be acting this way, therefore the force from the Sun must be greater. Okay, so that brings us to the end of ISP 3. I'm just going to put up the answers to the last couple of questions for those of you that don't have the ISP in front of you, so you can just double check them and read them through to make sure that you know what you've got. And remember to pause the video if you need to. Let me get to the bits. So this one over here was one that I went through. Yeah, went through those two there. Right, there's the ratio one. And there's the one which has been through there. Remember to pause the video if you need to check anything. Thank you very much for watching, guys.